Alright. So the last class we are discussing the topic. So can you hear me? Everyone can hear me. Can you hear me clearly? You can see.
Yes, sir.
Like so last class we are discussing about uh, rectifier with filter capacitor. So if you summarize what you learned about that in the last class, so if a typical rectifier with filter capacitor would look like that, if you start with, we just show the half wave rectifier. So we have got a half wave rectifier. Okay, so this is a capacitor C. Okay, and the load resistance RL. This is where we apply the VI, and this is the diode D. So then the voltage, which is their same node, if this voltage is VC and if this voltage is V naught, then in fact what? V naught and VC are same. So from there we know the output look like this. Okay, so first just for a half wave rectifier with filter capacitor, uh, V naught or VC, it should look like this. This is the output look like, where there's a maximum voltage which is VP. So we use a color, so VP, and then we have a minimum voltage and the maximum voltage, which we say is our VR. All right. Okay. So then we said that the expression for the ripple voltage VR equals to VP divided by FCRL. Okay. So that is for half wave rectifier. F is the value of the frequency, C is the value of the resistance, RL is the capacitor connected parallel to the resistor. In case it is full wave rectifier, then the expression for ripple voltage is Vp divided by 2FCRL. So these are the two expression for ripple voltage, one for half wave, another one for full wave rectifier. Now, in half wave, what is Vp? So Vp equals to Vm minus Vd. Vp is the peak maximum, we already said, the peak output. And Vm is input maximum. That's the thing you need to remember. Input maximum. Input maximum. So in case of half wave rectifier, half wave, it is Vm is equal to Vd. Then in case it is full wave rectifier, Vp is Vm minus 2Vd for full wave bridge rectifier. Okay, and Vp equals to Va minus Vd, the full wave rectifier with center tap transformer. Center. That's what it is.
স্যার এটা কি এই কোয়েশ্চেন গুলা কি ওই যে গতকালকে যে আমরা মানে লাস্ট ক্লাসে
আমরা
যে আমরা বের
এক্সপ্রেস
করেছিলাম?
করেছিলাম সেটাকে আমি রিভিউ করছি লাস্ট ক্লাসে,
জি,
আমরা ওইটাকে আমি জাস্ট রিভিউ করছি। And
ওকে।
you know why we have to VD for full wave bridge rectifier? Because each cycle we have to pass through, signal passes through two diodes. Why? Oh, there's only one VD because for each rectifier, uh, we have to pass through one dot. For example, let's say I have got this diagram somewhere here. I can find it if I let me find it. Okay. Okay. So I've got many diagram already drawn. I try to find them. Okay. Yeah. So it's a borrowed diagram from here. Now let this one. Yeah. So let's say I borrow this diagram. Copy. And then like. So that means if I want to, convert to a full wave rectifier with filter capacitor, what I'm going to do? I'm going to simply add a capacitor parallel to it. Let's say this is RL C. তাহলে কি দেখছি? For each half cycle, the diode has to pass through D2 and D3. For negative half cycle, diode has to pass through D4 and D5. Therefore, the corresponding two voltage drop. ঠিক আছে? Okay. So that are the general expression for all three types of uh, rectified with filter capacitor. আচ্ছা. Next হচ্ছে we learned about what ripple factor. So what is the ripple factor? Ripple factor we defined it as VR, which is the peak to peak voltage divided by VDC. Okay. So now what is that? We said that all right, we have VP defined, and then we have the VR, and then the average value should be running through the middle. So that is our VDC. Okay. So VDC, we found out that VDC, in fact, what? VP, the peak output, minus VR divided by 2. So we know VR, we know VDC, we can determine ripple factors. Okay, next, that's what it is. So next, let's solve a problem. Let's consider that we have to design a full wave rectifier that delivers peak current of let's say IL peak equals to 120 milliampere, okay, to a load mean করে আমরা resistor to a load RL. Okay, the peak output voltage VP equals to 12 volt, right? And then so the ripple voltage VR should not be much less than equal to 5% of input maximum. input max, which is our VM. And the frequency of the SIG is 50 hertz. I have to design it. So I need to determine. So what is the value of RL? What is the value of RL? And C that we need to select. So what is the value of R? That's our problem, is that I've got a rectifier, full wave rectifier, which is, I need to design it so that our output current is 120 milliampere flowing through the load. Peak voltage is 12 volt. This is the desired voltage. This is the peak output voltage that we want. Ripple voltage should not be more than 5% of the input maximum. 50%, what is that? Okay, it's a design problem. The first thing is that we didn't mention, we know that there are two types of rectifier. One of full wave rectifier. One of them is full wave bridge rectifier. Another is full wave rectifier with filter center tap transformer. We do it does the design problem. It didn't mention what types of rectifier we have to select. So we are free to select any rectifier. So let's say, since this diagram is already drawn here, let's consider a full wave bridge rectifier. Full wave bridge rectifier. So this is our desired rectifier. Okay, যেটা বলা আছে যে তার অ্যাক্রসে the load current, the VP হচ্ছে the voltage, the load current এর ভিতরে maximum current কত, IL flow করছে কত, 120 milliampere. It's a peak current. Now the question is, when do you think the peak current will flowing through the load? The peak current, I'm going to get it peak current when the voltage across the load is peak voltage. So when VP, the peak current flows when voltage across the resistor is VP. That's what it is. So therefore, I can easily determine the load resistance RL using Ohm's law, which is RL equals to VP divided by IL peak. RL যদি VP যদি পিক হয়, কারেন্টটাও হবে পিক হবে। কারণ আমার যখন ভিপি যখন মিনিমাম, লেটস সে ইফ আই গট দিস ভিপি ফ্লোইং, লেটস সে মিনিমাম ভোল্টেজ, তখন তো আমি ম্যাক্সিমাম কারেন্ট এক্সপেক্ট করতে পারি না। ঠিক আছে? সো আবার therefore I can easily determine RL. So which is 120 is a 12 volt divided by 120 milliampere. So volt into milliampere. So that gives us in fact 100 ohm. 100 ohm. So RL বের করে ফেললাম। আচ্ছা, তারপর হচ্ছে আমাকে কি বের করতে হবে? I have to determine the capacitor C. So what are the information that we have so that we can determine C? So one of the information is that I know the value of the resistance ripple voltage is, since it is full wave bridge rectifier, CRL. Okay, so this is one of the expression I can use. Then it says that VR should be what? VR should be, already mentioned, VR. So VR is less than equal to, it's a limit, 5% of VM. তার মানে হচ্ছে, if I can determine VM, then I can determine VR, which is, let's say I can select any value, because I can go for any value between 0 and 5%. This is the upper limit is 5%. I should not be, I cannot consider a VF which is more than 5%. It has to be less than 5%. Any value. Let's say VR is equal to what? VR is equal to, আমি ধরলাম যে I am free to choose. So let's say my VR is equal to 0.4, sorry, 0.04 times VM. তার মানে হচ্ছে I select 4%. আমি 5% সিলেক্ট করলাম না, 4% সিলেক্ট করলাম, because I can choose 4%, but I cannot choose select 5%. Okay. Now what is VM? We already know. So VM, we know that we already know VP is what? VM minus 2VD. Because this is the expression VM minus 2, we already consider the peak output voltage VM minus 2VD for bridge rectifier. All right. So that gives us VM equals to VP plus 2VD. VP তো আমরা জানি 12 ভোল্ট, আর VD হচ্ছে consider, if you consider silicon diode, it should be 2 times 0.7. That gives us 13.4 volt. So VP জানি. If I know VP, then what is VR? So 0.4, sorry, বারবার কি ভুল হচ্ছে, 0.04 times 13.4 volt. তাহলে আমি VR জেনে গেলাম. All right. Now I'm going to plug this value into this expression. Okay. So which is VP to জানি, VP is equal to, so I can write 0.04 into 13.4 equals to VP is equal to 12 divided by 2 into 50 into RL to বের করলাম 100 into, let's say I just use a different color representation. Now I can determine C. What is the value of C? That's it. Very simple problem. Actually, now if you are asked to determine the ripple factor. So what is the formula for ripple voltage? VDC. So VDC equal to VP minus VR divided. So VR jani, VP jani, I can determine VDC and simply V ripple factor. So VR divided by VDC. That's it. Very simple problem. Okay, any question?
No, sir.
Okay. Next, let's say in our class, last class, we discussed that, let's say we have got this signal. So that you see, that is coming from a, this is coming from, let's say, half wave rectifier. Let's say this is the half wave rectifier, or it could be full wave or anything, any half wave rectifier. Okay, so that's the output that is coming from a half wave rectifier. I don't need this. Okay. Okay. So this is the output here. This is the output we get from here, V naught. Let's say it is fluctuating between, let's say it is fluctuating between 9 volt maximum and the minimum voltage 7 volt. Okay, so that's the output from V naught. Now our objective is I want to get a output which is 5 volt. Output হচ্ছে say 5 volt. হচ্ছে V naught prime 5 volt চাচ্ছি অথবা closer to 5 volt, something approximately 5 volt DC. Remember I said that the role of engineer is to what? The role of engineer is to play with the signal. So so now I have to build a circuit. What should, my question is that what should I do so that this output, which is a rectified signal with filter capacitor placed across the load resistance. So what should I do so that I modify this signal so that it looks like this? What can I do? That's going to give you a constant DC, somewhere around 5 volt. This is an engineering problem. Engineering problem means I know what I want. I know what I want. I know 5 volt DC. I know what my input. I know the input is a rectified signal 7 to 9 volt. What should I do to obtain this? Well, one of the signal is that you have already remember. You can remember. Oh, remember we learned that if we use a diode, silicon diode, and if it is forward biased, so let's say we've got a circuit look like this. It's a silicon diode, and we have got a circuit like this. One diode. If we make it forward bias, any voltage. So let's say if I apply 2 volt. Okay, Vi is equal to 2 volt. Let's say R is equal to 1K. Then if I want to determine the output voltage V naught. So how can we determine? We know that we can, since it's a simple series circuit, we can apply Vp minus Vn rule to determine the current. We find that P side is connected to the positive terminal, N side is connected to the negative terminal. So therefore diode is forward biased. Okay, so diode is forward biased. Okay. So I can do what? I can replace the diode with a DC voltage source of 0.7. 0.7. তাহলে what is the output voltage we're going to get? বলেন তো? So what is the output voltage? What is the V naught? So that's our ground. Output voltage কত? V naught কত? It's the node voltage again.
Sir, 0.7
That's not 0.7. It's don't consider every problem is a device problem. The problem is the DC circuit problem. So V naught is 0.7. এখন বলেন তো আমি যদি 5 ভোল্ট চাই অথবা ক্লোজার টু 5 ভোল্ট হিয়ার, আমি কি করতে পারি? এনি আইডিয়া? আপনাদেরকে জিজ্ঞেস করছি। মানে what you can come up with any wild idea. After about whatever the idea you might be thinking in your mind, say, oh, might be too weird. Just let it out.
রেজিস্ট্যান্স কমায়।
What could you do? হ্যাঁ বলেন।
রেজিস্ট্যান্স কমায়।
Okay, we could do that. আর কিছু? আচ্ছা, খেয়াল করে দেখেছেন when I connected one diode I got 0.7। আমি যদি দুইটা ডায়োড যদি কানেক্ট করতাম তাহলে কত পেতাম?
1.4
1.4। নাও তিনটা ডায়োড কানেক্ট করলে কত পেতাম?
2.1
আচ্ছা, নাও think what I'm hitting. Let's say if I add 7 diode in series. Let's say I build a circuit like this. Okay. And then I have got one diode, then two diode, up to 7 diode. D1 to D2 to D7. D7. তাহলে and then if I take the output here V naught prime, এখানে কত পাচ্ছি আমার ভোল্টেজ? আমাদের ফ্লাকচুয়েট করছে কত থেকে? 7 থেকে 9। V naught 7 to 9 ভোল্ট। তাহলে দেখেন when it is 7 volt, what is the minimum voltage required to forward biased all the 7 diode? 4.9. So it is forward biased for 7 volt. It is also forward biased for what? 9 volt. So it doesn't matter what value we have. If you have 9 volt, diode is all the diodes are forward biased. If it is forward biased, what voltage we get? We get, so let's say for this we get so corresponding to this value we get 5 volt or 4.9 volt to be precise. Now I'm going to, so I said that approximately 4.9 volt. 4.9 volt. Okay. Now if it is a minimum a point, তাহলে কত? 4.9 volt or any value in between. 4.9 volt, any point in between. 4. So that is how we can get. So that's the basic idea. That is how we can convert an AC signal which has both positive half, negative half cycle absolutely into a DC signal. And there are in between we have this step. Now in reality we don't use diodes. In reality I could go for another circuit. So let's say there is one types of diode. So let's say as you are an engineer, you have to try to find different types of tools. I already said that the diode, BGT, MOSFET, there are tools, because there are tools that produce different types that allow you to modify the signal. I can, if you go into there's one types of diode which is called Zener diode. Zener diode, and the symbol for Zener diode looks like this. That's how it looks like. Zener diode is a very special types of diode. When it is forward biased, it behaves like a normal diode. That means I'm going to draw the IV characteristics, ideal or ID, okay, and ID or IZ here, okay. When it is forward biased, current is flowing from P side to N side. When it's reverse biased, current is flowing from N side to P side, okay. And when it is forward biased, it is plus positive, forward biased, and it is negatives, reverse bias. Now what I'm going to draw, I'm not going to draw the real IV curves, rather I'm going to draw the the constant voltage drop model. So what constant voltage drop model? IV characteristic is 0.7. If it's made out of silicon, 0.7 hertz forward bias. Interestingly, for reverse bias, it looks like this. Of course, control. Now, you see, when it is reverse bias, it behaves like a, for some certain value, it behaves like a normal diode, but at certain value, it enters into breakdown. So let's say this breakdown voltage is known as Vz, which is minus 5 volt. So that means if you apply a voltage which makes the Zener dot reverse bias, and you apply the voltage more than 5 in the reverse bias, then it enters into the breakdown region. When it's called breakdown region. So when it enters the breakdown, interesting thing happen. Okay. So doesn't matter what value you apply, what voltage you apply across it, the voltage across the Zener dot remain fixed, but the current through the Zener dot changes. For example, if you have got a circuit like this, let's me. Okay. So I use the circuit. Okay. Let's say we have got the Zener dot. Right? Now we apply 7 volt apply করলাম 7 volt. So for 7 volt, notice it is our N side. N side is connected to the positive terminal. P side is connected to the negative terminal. It's a reverse biased. Reverse biased. And also it's VZ equals to 5 volt. That means breakdown voltage. So breakdown voltage voltage 5 volt, which means if you apply a VI greater than VZ, then it will enter into the breakdown region. Once it's entered into the breakdown region, what happens? The voltage across remain fixed to 5 volt. তার মানে হচ্ছে current change হবে, কিন্তু value of the voltage will be 5 volt. So in that case, you notice what happens? For 7 volt, it sends the diode into the breakdown region, reverse biased, also in the breakdown region. So I can say as if the circuit looks like this. Circuit looks like this. Okay, as if I replace it with a DC voltage source of 5 volt. 5 volt. এখন 9 ভোল্টে যদি অ্যাপ্লাই করি তাহলে I'm going to find the same thing. So that means we're going to get constant 5. ঠিক আছে? So that's a very basic way to explain how we can modify the output signal so that it gives you a constant 5 volt. Now these types of problem I can give you a circuit like these things, I can give you the signal like these things, and I can ask you the output like this. So that I can give you, okay, how we're going to complete the circuit to get in 5 volt or 7 volt, anything like that. ঠিক আছে? So that is the topic from. So next I'm going to start.
Sir, can you repeat the breakdown region?
Breakdown regionটা হচ্ছে, it is, so when it is forward bias, we know that the current will be flowing through the diode, it's on. But normally we know that when it is reverse bias, no current is flowing. Like let's say if you have reverse bias, no current is flowing, no current is flowing, no current is flowing, no current is flowing in the normal reverse bias system. But if you apply a voltage such that the diode or the Zener diode is reverse biased, but the voltage is bigger than certain value. So let's say it is VZ is -5. Now if we apply a VI is equal to -7 volt. So VI is, in magnitude, VI is 7 volt and VZ is 5 volt. তার মানে হচ্ছে I apply a voltage more than 5 volt. In that case, the diode will no longer operate in the normal reverse bias region. Normal reverse bias regione আমরা কি জানি? Current is 0. No current is flowing. Then it enters into the breakdown. Once it enters into the breakdown region, you see that, let's say this is the point. We see I have a certain values of current. We call it IZ. Now, in that case, what is the current direction? Current direction, let's IZ1, it is from N side to P side. N side to P side current flow করে। তার মানে হচ্ছে তার একটা ভোল্টেজ আছে, তার একটা কারেন্ট আছে, like this. So same there should be current flowing N side to P side, IZ, okay, IZ, okay, let's say IZ1 or IZ1. So that's the thing. So we get a constant voltage, which is the voltage, constant voltage. See, what is the voltage? Constant voltage. What is the current? Constant. Variable current. Current may vary. আমি যদি 9 ভোল্ট দেই তাহলে আমার বেশি কারেন্ট ফ্লো করবে। আমি যদি 12 ভোল্ট দেই বেশি কারেন্ট ফ্লো করবে। But the thing is that voltage will remain fixed. So that's what it happens in breakdown region. আমি generally আরো হয়তো detail বলতে পারতাম, but I think that much should be enough. Is it all right?
Okay, sir.
Okay, thank you. Okay, so next topic is MOSFET. So this is our second device, and that's an important topic. And this is the topic that will be whatever the topic I will be able to cover till, and next week will be included to the midterm exam. So that's why I need to rush to introduce the topic. So it's a second device that we're going to learn in our course. The MOSFET stand for metal oxide semiconductor field effect transistor. Field effect transistor. Okay. So you see, how did you get the name? We use metal oxide semiconductor field effect transistor. MOSFET. MOSFET. Okay. Let's start with a very simple construction of the device. So we have got a it's a P-type material. We call it P substrate. That means there is plenty of holes inside the P material. So how do we get P-type metal? Every time we add one boron, we get one hole. So in P-type material, it is hole is majority carrier and electron minority carrier. So such as this, we have got a P-type P substrate. It's a block of P-type material which has plenty of hole as majority carrier and few electron as minority carrier. The next step is that inside this block we create two regions. Region 1, region 2. This region, it is N-type material. That is also N-type material. To be precise, it is N+. So N+ means here it is an N-type material where electrons are majority carrier, holes are minority carrier, but it has been heavily doped. That is plenty of, huge amount of phosphorus are added. To increase the carrier concentrations. Okay. So we have got P substrate. তার মধ্যে আমি দুইটা পকেট তৈরি করলাম. Now consider one thing. This is actually a three-dimensional structure. We have taken cross section. If you are that means if you look at the screen that you are using, part of the device entering is inside, getting inside the screen, or also coming out of the screen. Imagine that it is coming out of your screen as well as getting inside the screen, and we take a section. আমরা cross sectionটা দেখছি. Okay, so we have got p type region and the n type region, and then what we do, we in this region, between the two region of 2n plus region, in the p side, we deposit a very thin layer of oxide. This is silicon dioxide layer, thin layer of oxide, silicon dioxide insulator, which is an insulator. Okay, and then on top of that silicon insulator, we deposit a metal layer. Metal. Okay, so metal layer. ঠিক আছে? Then again here we take one metal layer, we deposit one metal and also another metal layer, and then we take 3 terminal out. That's it. That is our device. So insulator, so let's say silicon, that is our metal layer. All right, so that is the device. Okay, these 3 layers, 3 terminal are the 3 terminals of the device. One of them is called gate, and this one is called source, and this one is called drain. In short, we call it gate, source, and drain. Okay. So that's the very, and in that case, since it is p type, there is plenty of holes as majority carriers. Okay, plenty of holes as majority carrier. By the way, this region between this source and drain, it is known as channel, and length of the channel is L. Channel length is L. And also hole, as well as we have what? We have some electron as minority carrier. So we have got majority carrier, we have got minority carrier. Okay, first of all. So next, what we're going to do, first of all, 2 condition. Next, first thing we should be doing is that, so let's say 2 cases. Okay. First of all, we don't apply any gate voltage. So gate terminal, no voltage. And we connect the source terminal to the ground. And then we apply a voltage, positive voltage at the drain terminal. Let's call it VD. So we apply it at the drain terminal. Okay. This is the thing first we're going to see. So what is going to happen? Now also notice the source terminal is grounded. We can also, and then this is ground. So we can say, well, we call it say VDS. VDS. Okay. Notice, if you notice, আমি এই ডায়াগ্রামটা পর সেভ করে রাখি একটু সুবিধা হবে আমাদের জন্য কপি I leave it there. If you notice, between this is our n-type metal and which is surrounded by p-type metal. So what that means, we have a p-n junction. So that means between p side and n side we have a diode. As if we have got a diode. Similarly, between this n region is surrounded by p-type metal, so we're going to have a p-n junction diode. Again, we've got a diode, p to n. Right? So now if I draw the complete circuit, it should look like this. Start from here, the ground. Then it's connected to the source. Then it is connected to the diode. Then it's connected to the what? Another diode. From the channel, it's got another diode. And then it's connected to the drain. And which is connected to the DC voltage source. Okay. So that is how the circuit diagram is. So let's say this is our D1, this is our D2. So if this is the case, tell me what would be the current that will be flowing?
Sir, zero.
Zero. Because D1 or D2 are connected back to opposite direction. So in that case, in this case, this is our case one. So this is our case one. Case one. Okay. ID. Drain current is 0. So that is there is no conduction of current in the channel region. This is our channel region. So that is our channel region. So this is our channel region. No conduction of current in the channel region. This is our channel region. Now that can be, if this is the case, just for simplification, let's say it looks like this. That's what it looks like. Okay. As if it is a piece of insulator. Channel region, as if it is a piece of insulator. So there is no electron. Since insulator, there is no free electron. So insulator is like an insulator. Insulator. No free electrons. That's what it looks like. Okay. Case 2. Okay, case 2. Case 2. Same diagram, same connection. Now we do one thing. We apply a voltage at the gate. So case 2. Apply VGS. Okay, which is positive. So that we apply a gate voltage. That is our VGS. So VGS apply column. Now, if we apply this, then what happens? Okay, if you apply VGS, so that means what? It is our positive terminal, this is our negative terminal. So since the positive terminal, the voltage is connected to the metal layer, তার মানে হচ্ছে the metal layer will be, there will be plenty of positive charge distributed all over the metal layer. Okay, so positive charge connected to the metal layer, plenty of charge connected to the metal layer. Now this metal layer is going to do what? It is going to push the whole downward direction. Because it is positive and this is also positive, it's going to push the whole downward direction. Downward direction. As the holes are pushed downward direction, let's say if just slightly, so that's our let's say we have got enlarged this thing. This is our metal, the gate and oxide. Okay, and then we apply this voltage here. VGS, so plus minus, we have got positive charge distributed all over the metal layer, and these holes are pushed downward directions. If the holes are pushed downward, so remember that every time you add a boron, so boron atom, okay, so a holes is generated, and correspondingly the boron becomes negatively charged. As long as the positively charged boron, negatively charged boron ion and the holes are staying closer to each other, neutralized. If for some reason the holes move away, okay, তাহলে কি it is no longer neutral. Okay, so same thing happens. As the holes are moved downward direction, you're going to find you're going to have negatively charged boron ion, negatively charged boron ion, negatively charged boron ion. So the depletion region due to exposed boron ion, exposed, negative charge. So we're going to find exposed negative charge. So let's say negative charge. Okay. Now this positive charge push the whole downward direction, but it what does it do? It attracts the electrons towards it. So electrons are pushed towards the, because it is minority carrier or negative charge, it is pushed toward the oxide semiconductor interface. So we're going to find there are electrons accumulated underneath the oxide layer. So this positive charge on the metal pushes the hole downward direction. Therefore, we got a depletion of holes by exposing negative charge. At the same time, it attracts electron towards the interface. So we've got a layer of negative charge. Now imagine this scenario. So I draw these things again here. Okay. So as if we have got electron in the channel region. From there, okay, so that is our VGS equal to 0 insulator, and that's our VGS is equal to greater than 0. তাহলে কি we've got electron accumulated. তাহলে কি, what can I say? Isn't that become a conductive? This region become this particular region, this particular channel become is conductive. Now, if you apply a voltage, will the current be zero? Current will be non-zero. So you see, it's just two scenarios. On the left hand side, when VG is equal to 0, it's like an insulator. On the right hand side, it's like a conductor. Insulator or conductor. Channel, conductor. I'm talking about the channel, conductor. Channel. So how it becomes by inducing. So you can say a channel, conducting channel. So you can say a conducting channel has been induced. It's like a magic. I have the ability to change the conductivity of a region. If you, in terms of circuit, it's like an open circuit. Source, drain, and here it's like a normal circuit. So RCH, VDS. So therefore a current will be flowing ID, and ID is simply what? Applying Ohm's law, VDS divided by RCH. So this arrangement allows us to modify the conductivity of the region. That's why this is called transistor. Transistor means transfer transistor. Transfer resistor. I can modify the conductivity of the region. It become open circuit. Off, that is actually called cutoff. That's a cutoff. This cutoff. Or this is our on situation. Okay, so that's what, by what I did, I managed to conduct current from channel, from source to drain by applying gate voltage. Just gate voltage is like a key. That's a very good analogy of this. So if you consider it's water tap analogy, let's say we've got an water tap, right? So we have got a key here. Okay. So that side is, connected to the supply main. This is connected to, that is our source of electron. That is our drain. So you can imagine the water is coming as drain, and this is our gate. If it is all the way closed, no water. If it is all the way open, the maximum amount of water. So that's what we do. Just changing the voltage gate voltage. I can make the channel region insulator or channel region conductor. That's the basic principle, or the basic, fundamental way the MOSFET operates. That's the simple way to explain these things. Now we are going to, as we know that as an engineer, we're going to find out the IV characteristics, how the voltage, VDS, and the current source, current IDs are connected. Okay. Now, the thing is that, so we know that VGS greater than 0 hole, we have a scenario that channel conductivity change. But it doesn't mean that as soon as you apply any gate voltage greater than 0, it's going to start conducting. It's not like that. There should be a minimum value of voltage. Minimum voltage. So when applied, sufficient numbers of electrons accumulated underneath the oxide layer. So if I keep on increasing the voltage, okay, you would say more electrons will be attracted. Higher the VGS, higher VGS, higher VGS, VGS, higher electron accumulation at the oxide semiconductor interface or the channel region is more. Because as you have applied higher voltage, that is going to attract more electrons. Now, once the thing is that, the question is that the electron will be accumulating there. But since you have got an oxide layer, electron cannot penetrate this oxide layer. ইলেকট্রন গুলি কি এখানে যাবে ঠিকই, ইলেকট্রন গুলি যাবে ঠিকই, এখানে গিয়ে আটকে থাকবে, because it's an oxide layer. It cannot pass through the oxide layer. That's when the gate current IG, gate current is always zero. Gate current is always zero. Always zero. Current cannot pass through. Okay, so certain value it start to conduct. So this value is called threshold voltage, VT. VT or threshold voltage. So what is the definition of threshold voltage? The value of VDS, VGS, at which sufficient numbers of electrons accumulate, okay, under the oxide layer to create a conducting channel. Channel is known as threshold voltage, VT. VT. তার মানে হচ্ছে what is the value of VT at which it will be conducting. Okay. Okay. So next topic that would be, I'm going to find out the IV characteristics. First of all, we try to find out the relationship between ID to VDS for different values. For example, let's say we have got a MOSFET. Okay. We apply a gate voltage VGS, which is greater than VT. Greater than VT. তার মানে হচ্ছে কি, we have got so this is our source and this is our drain. Okay. So we know that a channel will be created. So this is the channel. So this is channel depth. Channel depth means we've got so we've got plenty of electrons. Accumulate. Now, first of all, we consider the drain is VDS is small VDS. Okay, use scalar VDS. তার মানে হচ্ছে VDS is let's say 0 to 300 millivolt. So তার মানে হচ্ছে এটা আবার যদি 0 হয় up to this point, so let's say 300 millivolt. এই রেঞ্জের মধ্যে কি হচ্ছে আমার এই রেঞ্জ এই যে ইনিশিয়ালি I can apply smaller gate voltage, drain to source voltage. I can apply bigger drain to source voltage. Now I'm going to start with, at this case I'm going to say what happens, but I'm not going to say why it happens, right? So at that voltage you see that this is our see this is our source end, and this is our drain end. So channel thickness, channel thickness at the source end and channel thickness at small voltage, channel thickness at the small source end and the channel thickness at drain end are same. In that case you're going to find out the current will change linearly. Let's say this is how it looks like. Let's say this is the channel depth, this is our channel region, and we already said this is our channel region is a, I would say the entire structure is a three-dimensional structure. This is the length of the channel, okay, and this is the width of the channel, and this is the depth of the channel. Okay, so this is our, and then let me draw the circuit. This is connected to the source, and this is our other side, VDS. Okay, so now the question is, for small values of VD, channel depth at the drain end, channel depth at the source end and channel depth at the drain end are same. In that case, the resistance RCH of this region, okay, will be constant. So we can determine the current ID, let's say ID1 is our VDS1. Let's say we apply VDS1 divided by RCH. Okay, or let's say RCH1. Then current key, current is proportional what? ID is linearly proportional to VDS. So I can say the IV characteristics look like this. Okay, this is for small value, so linearly change করছে। এখন যদি আমি একটা সিনারিও করি, let's say if I apply little bit more gate voltage, so go more gate voltage হলে কি হবে, আমার চ্যানেলের ডেপথটা কি আরো বেড়ে যাবে না? So more electron will be occupied here. So how can we express these things here? Okay, আচ্ছা এখানেই করি। So we need to draw it separately. So channel more voltage, so channel depth বেড়ে যাবে, channel depth will increase. So channel depth যদি বেড়ে যায়, আমরা কি জানি, the cross sectional area কি কমে গেল না? So RCH is inversely proportional to the cross sectional area. তাহলে the second resistance RC cross sectional area বেড়ে গেল, resistance কমে গেল, তাহলে ID2 you can say same voltage যদি apply করি VDS1 and in that case RCH1 RCH2. Now we know that RCH2 is less than RCH1, that is the previous resistance. So আমার কারেন্ট বেড়ে গেল, তার মানে হচ্ছে we'll find the output look like this. Okay, next. এখন যদি if I keep on increasing the voltage, আমি যদি ভোল্টেজটা এইখানে লিনিয়ারলি কাজ করছে, আমি যদি ভোল্টেজ একটু বাড়াই, if I let's say apply this voltage, in that case VDS যদি একটু বাড়তে থাকে, then we're going to find out VDS যদি একটু বাড়তে থাকে, VDS will no longer remain uniform. VDS will be like this. Source end, at the source end, the channel depth will remain the same, but the drain end, the channel depth will taper off. Channel depth কি করবে? আর ইউনিফর্ম থাকবে না, আস্তে আস্তে কমতে থাকবে, like this. So in that case, you will find out that current is going to increase, all right. Current is going to increase. আমি এটাকে ইউজ করি, but current will become slowly increase করবে. See, it will no longer is going to increase linearly. Rather, the current will increase, all right, but current will increase of the current will become slow. আমি যদি ভোল্টেজটা আরেকটু বাড়াই, let's say এই ভোল্টেজ দিলাম, then you're going to find that the channel depth will at the source end will remain same, but the channel depth at the drain end exists. You see, you have channel exist at the drain end, but the depth will decrease. You're going to find out current will become even more slower. আরো কমে যাবে। তার আরো যদি VDS apply করি, let's say this value, তখন কি হবে? In that case, you will find out the channel is going to have a such scenario that at the drain end, it barely touches the drain end. Okay, in that case, so that's what it looks like. If I keep on increasing the VDS, increasing, so if find the drain exists, channel exists at the drain end, but gradually the depth of the channel decreases, and correspondingly current will become slow. At that point, we're going to find a scenario that it looks like this. So you see the current initially changing linearly, and the current তারপর কি changing very slowly. At some point, it is going to reach this point, and this is the maximum current that we can have. Maximum current. Okay, let's say this is our A. Then let's say, sorry, A, B, and then C. তিনটা position. Here is one. A, B, and C. তিনটা. Just this is the value of current A corresponding the position of the channel depth at the drain end A. This is the channel position B and the corresponding current, and the channel position C and corresponding current. Now at C, maximum current occurs. This is at maximum current. This is the current at maximum current occurs. This region is called pinch off. The position C, pinch off of region, and maximum current, maximum drain current. Is the maximum drain current that could happen. Now the question is, can I increase VDS even more? Of course, let's say I increase the VDS like this. You consider, let's say I increase VDS to this value. VDS to VDS value. Then what would be the current? Let's say if this is the case that happens, VDS, then you're going to find the channel will not, let's call it our D. Let's call it our D. So position D. The channel doesn't, the channel doesn't exist at the drain end. Channel cease to exist. Channel terminates here way before it reaches the drain end at position D. Position D. Channel doesn't exist at the drain end. Then the question is, what will be the current? Current will be interesting. Current will remain whatever the current, whatever the maximum current we obtained at that C, that will be the current D. That will be the current. So that is how the IP characteristics look like. So for different values of VDS, we see the current. That is for different values of VGS. Let's say this is our VGS2 and VGS1 এর ক্ষেত্রে আমরা এরকম জিনিস দেখতে পেতাম। VGS1. Now notice one thing. If you look at this curve, let me draw it here. If you look at this curve, if you just the top curve, okay? So the top curve, it looks like it has two part. One part is when current is increasing, one part is current is constant. তাই না? If I divide it in two parts, current increasing, current ID increasing, and ID constant. So that's the ID increasing part and this ID constant part. Now there is a relationship between current increasing with the current in a channel position at the depth, channel position. So current, when current increases, current increasing, ID increasing, ID increasing is related to, is associated or related to having channel at the drain end, like A, B, C, A, B, C position 3. ID constant. It's like what? Channel doesn't exist at a channel doesn't exist at the drain end. Channel exist at the drain end, like which was our position D. So I can relate the channel increasing with having the ID increasing having the channel at the drain end. So that's how we can relate. আমি আজকে এতটুকু পর্যন্ত পড়াবো। So next class we're going to move. Any question? Any question?
নো স্যার।
স্যার ট্রান্সফার রেজিস্টরের পার্টটা আবার একটু রিপিট করবেন।
I was saying that actually that's, you see what I did, what we did. See, I hope you are got that point, that if I apply voltage at that gate, then by applying voltage I can change the conductivity of the channel region. When there is no gate voltage at the, it's like an insulator, so there should not be any current flowing from drain to source. On the other hand, when you apply a gate voltage, which is VGS equal to 0, in fact, we have to have a, to be precise, we have to have VGS greater than equal to the threshold voltage. তাহলে we have sufficient numbers of electron accumulate in the channel region, so therefore its conductivity has changed. So therefore it looks like an insulator when it's VGS 0, and it's like a normal resistor when it is gate voltage more than 0. তাহলে আমি এই রিজনের চ্যানেল রিজনের রেজিস্ট্যান্সটা আমি চেঞ্জ করে ফেললাম না বাই অ্যাপ্লাইং ভোল্টেজ। সো আমি ভোল্টেজ অ্যাপ্লাই করলাম এক জায়গাতে, ট্রান্সফার করলাম আমি ভোল্টেজ রিমোটের মতো। at some places I apply gate voltage and somewhere else a resistance has changed. That's why it's called transistor. ট্রানজিস্টর ট্রান্সফার রেজিস্টার, ঠিক আছে? Okay, any other thing? Okay, if you don't have any issues, so what you can do is just write down your ID in the chat box there for your attendance. And then you can take leave.